think we finally got it. All right, so this topic is solving higher degree polynomials. And my target is, and the only thing I don't like about these new notes is I don't have a place for like my essential question or my target or whatever. So that's okay. We can utilize the space up top. And I'm going to call it a target since that's what the county calls them now, are targets. How do you determine it's not what? Oh, how do I get the third from? Yes, thank you. It is the 7th. How do you determine how many roots a polynomial has Somebody get that, please. How do you determine the signs of the real roots? What?
That's for Janaya.
Oh, okay.
And then, yeah.
Thank you. Bless you. Running out of room here. And how do you determine all possible rational roots, which I got to fit in this little space up here? How do you determine all possible rational roots? So my notes already look messy, but what do you do? How do you determine the signs of the real roots? This part, second question? Is that what you asked? Yes. Yeah. That's what I asked. Okay, so you know we know how to solve a lot of equations. We know how to solve linear equations. That's when you just have 1 degree. Samantha, can you put that in your backpack? We just solve for x, right? We know how to solve quadratic equations. That's what we spent a whole lot of time on. That was mostly what section 4 was about. You can solve by factoring. Set each factor equal to 0, solves for x. But factoring doesn't always work. You can solve using the quadratic formula. That always works. And you can solve by completing the square. That always works. If it's a quadratic polynomial that you're trying to solve. Okay, but not everything's quadratic or linear. We've got polynomials with 3 degrees. That's called a cubic polynomial. Polynomials with 4 degrees. That's called a quartic polynomial. Polynomials with 5 degrees. That's called a quintic polynomial. And then 6 degrees, 7 degrees, 8 degrees, I don't think they have special names, but it doesn't matter. There's lots of polynomials other than just linear polynomials and quadratics, okay? So what I'm going to teach you today is how to determine the solutions when you have a higher degree than 2, okay? So we're going to do mostly 3 degrees, and we'll throw in a 4th degree polynomial, but we don't really have to go higher than that, okay? You'll do that in college. All right, so there's some theorems and some rules that we have to use to help us determine what our roots are. And the first one is called the fundamental theorem of algebra. And I'm not going to underline and highlight the important stuff because that's what you're supposed to do when you're going back and doing your summaries and doing your questions on the side. You're interacting with your notes and you're looking at the important parts. That's a good time for you to highlight and whatnot. So the fundamental theorem of algebra states that a polynomial function of degree n has exactly n zeros in the complex plane. Which we've talked about this before, I just didn't tell you the name of the theorem. If we have a quadratic, we know that it's not going to have any more than two solutions, right? Because the solutions tell you where the graph crosses the x-axis. Well, quadratic can't cross the x-axis more than 2 times, right? So, 2 solutions that it can have. It could also have 1 solution, or it also could have 0 solutions. 2 solutions or 0 solutions. If it has 1 solution, it's technically 2. It's just that the solution repeats itself. So it still counts as 2, even though it only crosses the x-axis once. If I have a polynomial of 3 degrees, that means I can have up to 3 solutions, no more. If I have 4 degrees, I will have 4 solutions. 5 degrees, 5 solutions. Altogether, that includes real and imaginary. So say I had 4 degrees. I might have 2 real solutions and 2 imaginary solutions, but I'll have 4 altogether. Okay? So that's what the fundamental theorem tells us. The zeros of a polynomial are also called the roots of the equation, which we already knew that. Usually, a lot of times you'll hear them say, what are the solutions? But remember, we also told you that they're also called roots and they're called zeros. It means the same thing. Real zeros of a polynomial are points where the graph intersect the x-axis and y equals 0. Again, that's review. We already know that. We know solutions are where a graph crosses the x-axis, right? Are real solutions. If they're imaginary solutions, that they don't tell us where the graph intersects the x-axis. Only our real solutions do. And solutions are called zeros or they're called roots. We know that. Real zeros are called complex zeros since every real number is a complex number with an imaginary part equal to 0. So basically they're saying if you had a real number of 5, we usually just call that a real number, but we could call it an imaginary number. It's just that the imaginary part would have, you know how we have a plus bi? That's a complex number. A is the real part, bi is the imaginary part. So if you just had a real number, we could call it complex, but that b would be a 0. So like 5 plus 0i is the same thing as 5, right? Because 0i would just turn into 0. So that's all that's saying. And then one more thing to know about the fundamental theorem is that complex zeros that contain an imaginary part not equal to 0 are not visible on the graph. Nope, sorry. So it's saying if you have a complex 0 and the imaginary part is not 0, but it's like 4 plus 3i, that kind of complex number, you're not going to see that root on the graph. So that's what you need to know about fundamental theorem. The next thing we have is Descartes' rule of signs. Kind of looks like Descartes' rule of signs. I've always heard it pronounced Descartes' rule of signs. I'm sure people did pronounce it different ways, but that's how I've always heard it pronounced. Descartes' rule of signs. And Descartes' rule of signs can be used to find the number of positive and negative real zeros of a polynomial function. Everybody have that? Before I flip the paper over? So I have more stuff to write about that on the back side. So the fundamental theorem tells us how many roots we're going to have altogether. Real, imaginary, total number. Okay? Descartes' rule of signs tells us how many positive real roots we'll have, positive real roots, and how many negative real roots we're going to have. It doesn't tell us anything about our complex solutions. It's only about the signs of the real roots. Okay? So, well, how do you know? That's what I'm going to tell you on the back side of the paper. So I'm going to put a little arrow down there. The number of positive real zeros I told y'all these notes were going to be lengthy, and I might not have mentioned boring, but they are really good information that we've got to have. The number of positive real zeros of a polynomial function f of x is the same or less than by even numbers bless you, as the number of changes in the sign of the coefficients. And we're going to do several examples of this, so if you have no idea what that definition means when we go over it and with actual problem, it'll make more sense. But when I give you a polynomial and you look at each term in the polynomial, anytime it changes sign, so like the first term's positive, the next term's negative, that counts as a sign change. Okay? If you go from a positive term to a positive term, that's not a sign change. Positive term to a negative term, sign change. Negative term to a positive term, sign change. Okay? So however many sign changes you have is going to tell you how many positive real roots you're going to have. So say you have 4 sign changes. That means you're either going to have 4 positive real roots, or you reduce that number by 2 for the possibilities. Or you'll have 2 positive real roots, or you'll have 0 positive real roots. Okay? One of those. But if you had 1 positive root when you got your answers, something's not right. So if you have a quadratic, okay, say you had 2 sign changes, that means you're either going to have 2 positive real roots or 0 positive real roots. One or the other. Can't have just one if you have 2 sign changes. Does that make sense? All right. So the number of negative real zeros of a polynomial function f of x is the same as or less than by even numbers as the number of changes in the sign of the coefficients of the terms of f of negative x. So the number of negative real zeros in a polynomial function f of x is the same as or less than by even numbers as the number of changes in the sign of the coefficients of the terms of f of negative x. So what that means is you look at your original problem and see how many sign changes you have to find your positive real roots. Then take your original polynomial, wherever you see an x, substitute in negative x, and then you got to simplify because you're going to have exponents and coefficients. Go through and simplify that, and then after you do that, count the sign changes after you substitute in negative x. And it doesn't just make everything opposite of the original because exponents. So you evaluate that and see how many sign changes you have. Okay? Same as with positive. If you have 2 sign changes once you substitute in the negative x and simplify, then you'll either have 2 negative real roots or 0 negative real roots. But you don't look at the original for negatives. Okay? You got to substitute in negative x. And that is Descartes' rule of signs. All right? Fundamental theorem tells you how many roots you have total. Descartes' rule of signs is about the signs of the real roots. That's what that tells you. And the final definition or theorem, rule, whatever you want to call it, is the rational roots theorem. And I went back on the front, the fundamental theorem of algebra, and I put a box around that to make it stand out that because I have 3 different main topics in these notes. Okay, so the rational roots theorem is going to tell us what are all of our possible rational real roots. Not just real roots, because the square root of 2 is a real root, but it's not rational. All right? Rational is a fraction or a number that you can turn into a fraction. 2/3 is rational. The number 3 is rational because can't I put it over a 1 and it's a fraction, right? But the square root of 2 is this number, and it keeps on going. It does not terminate. The only way to turn that into a fraction is if I rounded it. All right, so the square root of 2 is not considered rational. If you have to round it to turn it into a fraction, we don't call that a rational number. So like the square root of 2 is a real number, square root of 3 is a real number, but they're not rational. So this list only tells us our possible rational real roots. Okay? All right, the rational root theorem states that if P of x is a polynomial with integer coefficients and if P of Q, or I'm sorry, not P of Q, P divided by Q is a 0 of P of x, then P is a factor of the constant term of P of X and Q is a factor of the leading coefficient of P of X. Example, 2x to the fourth plus 2x cubed plus 8x plus 5. So again, rational root theorem, it's going to give me a list of possibilities of my real roots, my real rational roots, okay? All of these possibilities are not answers. They're not all roots. It's just possible roots. It's a good place to start. We have to have somewhere to start. It's totally different than the quadratic formula, factoring, completing the square, okay? Every other degree higher than 2 doesn't have a special formula to solve it. All right, so we have to have these roots and theorems to help us figure out some possibilities to give us something to go with. So what you do is, all right, so it talked about P divided by Q in there. Your P is whatever the constant is. Remember, constant is the term that does not have a variable. Okay, in standard form, it will always be the last term. If you don't have a constant, if your constant is 0, you're not going to see it, but that's still your constant. Q, as long as this is in standard form, it's whatever the coefficient of the leading term is. So P is 5, Q is 2. So first thing you do is find your factors. Doesn't matter if you find the factors of P or Q first, but I do factors of P first because in the end you have to do P divided by Q. And the way I set it up, the P's are on top of the Q's. I don't know, it just makes more sense to me. Factors of P, and you're doing the positives and negatives. So what numbers are divisible? What are all the numbers that go into 5 easily? Evenly, not easily. 5 and 1. Positive 5 goes into 5. Negative 1 goes into 5, right? So the way you would write it is 1's a factor of 5, negative 1 is a factor of 5. So positive, negative 1. 5 is a factor of 5, negative 5 is a factor. So positive, negative 5. You don't want any decimals, just integers. Anything else? No. Then you find your factors of Q. Your Q is 2. So what are all the numbers that divide into Q evenly? Positive, negative 1, and positive, negative 2. So this is not the list of possible factors. Your list comes from when you divide P divided by Q. So all possible rational roots, you have to do P divided by Q, and that will give you all of your possibilities. And sometimes they're the same as the factors of P. If Q is just 1, then it'll be the same as the factors of P. Bless you. All right, so I have to find every combination. What's 1 divided by 1? 1. So that P divided by that Q is going to be positive, negative 1. Now, do 1 divided by 2, we get 1/2, right? So positive, negative 1/2. That's a rational number. It's a fraction. 1 is rational because I can turn it into a fraction. Now let's move to 5. 5 divided by 1 is 5, so we'll have positive negative 5. And then 5 divided by 2 is 5, just leave it 5 halves, positive negative 5 halves. So how many roots should we have altogether? When we actually solve this, or if we were going to, how many roots would we have altogether? 4, real and imaginary. You might not have any imaginary, okay? 4 altogether. We just found a possible list of 8. So all of those they can't be actual roots. But if we're going to have a real root that's rational, it will be in that list somewhere, okay? And you'll see when we actually solve them, that's where we're going to start. We're going to start looking at our possibilities. How many sign changes do we have? This goes positive. Your first term's positive. Positive to positive. Is that a sign change? No. Positive to positive. Is that a sign change? Positive to positive. Is that a sign? We don't have any positive sign changes. So that means we will not have any positive real zeros. So if I were going to test this out, all of the positive numbers, I wouldn't even try because I'm not going to have any positive roots, so they're not even going to make the list. Okay? We're not solving this one. So, and if I wanted to know how many negative real roots I would have, I would put in negative x, negative x, negative x, simplify with the radicals, multiply by the coefficient, and go from there. But I'll save that for in the actual example. All right, is everybody cool? Okay. So, let's do an example and see what in the world. I'm not going to relabel the top. I'm just going to put continued because it's the same notes. Okay. Example 1. Find all solutions, or I'm going to say roots. Find all of the roots of f of x equals x cubed minus 2x squared minus 5x plus 6. So we're going to go through that whole process. We're going to figure out all of those characteristics of this function before we actually try to figure out what the roots are. Okay? So the first thing I'm going to look at is I'm going to try to determine the total number of roots. How many roots am I going to have? Anybody know? Fundamental theorem helps us with this. Draw it a guess.
500.
No. 3. My highest degree is a 3. That tells me how many roots I have. So 3 altogether, and that comes from the fundamental theorem. 3 roots altogether. Your highest degree tells you your number of roots altogether, real and complex. Okay. Now I want to know the number of positive real roots. And for that, that's from the Descartes rule of signs. I have to look at the sign changes of my original problem. Okay. So, and don't forget your first term. A lot of kids do. My first term's positive. My second term is negative. Is that a sign change? Yeah, so I count that as one sign change. And then I go from a negative term to a negative term. Is that a sign change? No. Nope, that doesn't count. Then a negative to a positive. Is that a sign change? Yes. So I have 2 sign changes. That means I can have 2 positive real roots, or you reduce that possibility by 2. So I'm either going to have 2 positive real roots, or I will have 0 positive real roots. I keep saying real. No, I said it right. Positive real roots. 2 positive reals or no positive real roots. Okay? Everybody cool with that? And then for the number of negative real roots, that's where I'm going to take my original, but wherever I see an x, I'm going to substitute in a negative x and simplify. So instead of x cubed, in parentheses, that'll be negative x cubed because I'm raising the negative and the x to the third power. Minus 2 times negative x quantity squared minus 5 times negative x plus 6. Now when you raise a negative to an even number, negative times a negative is a positive. Negative times a negative times a negative times a negative is a positive, right? So a negative raised to an even power changes the sign. How about if you raise a negative to an odd power, like a negative raised to the third power? That's a negative times a negative times a negative. It's a negative. What about raised to the fifth power? Negative. Negative times negative times negative times negative, negative. So when you're raising a negative to an odd power, it's going to stay negative. When you're raising a negative to an even power, it'll change to positive, right? So we got to simplify this. So negative x quantity cubed, does that stay negative or positive? Stays negative. And I'm going to keep it in the parentheses because I'm not just raising x to the third power, I'm raising negative x to the third power. All right, over here, don't do negative 2 times negative x first because exponents come before multiplication. Negative x quantity squared changes to positive x squared times the negative 2 coefficient is what? So negative 2x squared. Negative 5 times negative x, positive 5x. And then the 6 doesn't have any x's, so just bring down a plus 6. Okay? So, I have a negative to a negative. Is that a sign change? No, doesn't count. Negative to a positive. Is that a sign change? Yes. Positive to a positive. Is that a sign change? No. So we're either going to have one negative real root, or if I reduce that by 2, I get a negative number. I can't have a negative number of negative roots. So it's 1. If I do not have one real root, that's it, no more, no less, then something's wrong. Either I messed this up when I counted or when I substituted my negative, or something was wrong with my math when I found my roots, okay? So this came from Descartes' rule of signs. And then the last thing that I want to look at before I go and actually try to find my solutions is I want to determine all of my possible rational roots. And of course, that comes from the rational root theorem. So let me just rewrite my problem down here. F of x equals x cubed minus 2x squared minus 5x plus 6. And my P is 6. And my Q in this case would be 1. So to find all your possible rational roots, you have to find the factors of P, then you find the factors of Q, and then you get all the combinations of P divided by Q. Y'all cool? Exhilarated by this knowledge? That's what I thought. All right, so factors of P. I like to list them least to greatest. Yeah. Make sure you look at your original. A lot of people were making the mistake of looking at down here once we substituted in the negative x. Make sure you look at the original. Okay, because that's an easy mistake to make. Let me just double check. X cubed minus 2x squared minus 5x plus 6, yeah. Okay, factors of 6, least to greatest, what do I have? Yep. 1 and 6, yeah. And you don't even have to think of it like that. Just think of all the numbers that go into 6. Because 1's a factor of 6, 2's a factor of 6, 3, you know what I'm saying? But you could do it that way as well. Just you want to make sure you don't leave anything out. So I like to think of what are all the numbers that divide into 6 evenly. Okay? So I know positive and negative 1, positive and negative 2, positive and negative 3, and positive and negative 6. Factors of Q, well, that's easy. What do I have? Positive and negative 1. So when I do P divided by Q, since Q is a 1, 1 divided by 1 is 1, 2 divided by 1 is 1, 3 divided by 1 is 3, 6 divided by 1 is 6. So it's just basically going to be the same as the factors of P, right? But if Q is any number other than 1, then you're going to have probably some fractions in there. So this is the list where I get my possibilities from. Not the individual factors, but you have to do P divided by Q. So basically we use the rules and theorems that we found in the first part of the notes. So now we're going to actually use that information to help us figure out what are the actual roots. We know there's going to be 3 of them. We have to find them. Okay, do y'all remember when we learned how to do long division of polynomials? Remember that? Draw a line, change the sign. Remember all that? Okay. Well, there was another way to factor called synthetic factoring that I did not teach you at the time. Synthetic factoring does not always work. It only works when you have a linear divisor. So the way I taught you, long division always worked, okay? Synthetic division does not. But we're going to use synthetic division, so I'm going to have to teach you how to do it now. We're going to use synthetic division to help us figure out if any of these possibilities are actually solutions or roots or zeros, okay? So we are going to use synthetic division to determine if any of the possible rational roots are actual roots. So I have 8 possibilities to choose from. 8 possibilities. There's no, you just pick which one you want to start with. Okay, there's no secret to figuring out which one to start with. So you just start. What do y'all, give me one to start with. 1? Somebody say 1? Okay, I'm going to try 1. So let me go ahead and write my function down here again so I have it near, because I want you to see where I get these numbers from. You've got to pay attention to how I do this, because solving using synthetic division is something new. We've not done it before. And you can't just look at it, probably, and figure out how I did it. If you're not paying attention and you go back later and you see all these numbers, it's not going to be obvious as to how I got the numbers. Okay? So what you do is, if I want to know if 1 is a root, I put 1 and I put it behind, I call it behind a little house or behind a little wall. Okay? So I want to know, is 1 a root? Then I look at my function, and first of all, make sure I'm not missing any degrees. If 3 is my highest, I should go 3, 2, 1, 0. I go 3, 2, 1 and a constant has 0 degrees, correct? So I'm not missing any, so that's good. If I was, I would need to put in a placeholder just like I did with long division. So now you just take the coefficient of each term. So what's the coefficient of my first term? 1, and then -2, and then -5, and then 6. This is like a shortcut way to long division, okay? You skip a line and you draw a line. All right.
So you just get rid of like the variables and exponents?
Yes. Okay. All right. To start it off, the very first number, you just drop it down below the line. And we got to figure out what numbers are we putting here. Okay. So the number you drop below the line, that's your starting point. You multiply that by whatever the number is behind the little house. So 1 times 1 is 1, and it's positive. Now once you get a number here, these two numbers you add or subtract, whatever the sign is. So a -2 and a +1 make what? -1. Then you start the whole process all over again to get the next box, okay? -1 times the one behind that little house is -1. That goes in the next little box. Then you add or subtract. -5 minus 1 is -6. Then you multiply. -6 times +1 is -6. Add or subtract. 6 minus 6 is 0. We got very lucky that the number we picked worked. How do I know it worked? Well, whatever this last number is your remainder. Remember when we did long division, if your remainder is 0, then we knew whatever our divisor, whatever we were dividing by, was a factor. Do y'all remember that kind of? It was like way back at the beginning of the school year. I could show you in my notes. So if we get a remainder of 0, that tells us that 1 is one of our roots. Okay? If our remainder is anything other than 0, then we got to pick another number because we did not find a root. Okay? So let's make a little explanation. When the remainder is 0, then we know we found an actual root. So of the 3 roots that we need, number 1 is one of them. You're like, well, when we did long division, there were x's and stuff in our answer. True. Okay? We just haven't written that part of it yet. We just know the coefficients of each of the terms. Okay? So what we need to do, if we know this is a root, if it's not, move on. I don't care what the x's and stuff are. Okay? But if we found a root, we want to, what you do is, if my original polynomial has 3 degrees, take 1 off of that, 2 degrees. So this is like, what we're actually doing is like factoring out a factor and seeing what's left. Common factor, think about it like that. So if this is 3 degrees, then this term will be a quadratic term. It'll have 2 degrees. So this is like 1x squared, and then you go down. So the next term will have 1 degree. So minus 1x minus 6. So 2, 1, 0. This is called a reduced degree polynomial. A reduced degree polynomial. And we can use that polynomial to help us find more roots. Well, notice sometimes if we started with 4 degrees, our first polynomial that we could create would have 3 degrees. Okay, we would want to reduce it again using division. But We only started with 3 degrees, so when we got a reduced degree polynomial, it had 2 degrees. Do we know how to solve a quadratic? Yeah, we don't have to use long division anymore. We know how to solve a quadratic. So we can try to solve it by factoring, completing the square, or quadratic formula. So let's see. Use the reduced degree polynomial to help find the other roots. In this case, we have a quadratic polynomial. So we can solve by factoring. In parentheses, I'm going to put if possible, because factoring is not always possible. The quadratic formula. Or completing the square. And some of you, I know y'all are real particular about your notes. You don't like them to look all jumbled up and stuff. If you want to take these notes on regular paper, but still set it up like Cornell notes, so give yourself that left-hand column to write stuff in and give yourself at the end a summary and put it on regular paper instead of this paper that I give you, I'm totally fine with that. All right, so I'm going to try factoring. And I don't need 1x squared minus 1x minus 6. Isn't that the same thing as x squared minus x minus 6? And I'm going to set it equal to 0 to solve, because I want to know when y is 0, what is x? So if I'm factoring that, does it have a greatest common factor? Does it? No. What is A? 1. What is B? -1, and what is C? -6. All right, we'll make our little t-chart. We need two numbers that multiply together to give us AC. A times C is -6. And we need two numbers that add to give us B, which is -1. What you got? All right, let's try it out. -3 times +2 is -6. -3 plus 2 is -1. Does that work? Yes. So we know from here, if we're factoring, we make our parentheses. We did not have a GCF to go on the outside. The variable being used in this problem is x, so that's our first term in each set. Look at your t-chart to find the numbers to be the second term. We've got a -3 in one, +2 in the other. Is it necessary to divide and slide using this problem, on this problem?
No.
No. So we know 2 degrees is going to give us how many solutions? 2 solutions, right? So if I set x minus 3 equal to 0, what does x equal? 3. There's one solution. If I set x plus 2 equal to 0, what does x equal to? -2. There's the other solution. So I have now found 3 roots. I found that one when we did synthetic division, right? I have +3 and -2. So I like to list them least to greatest. So that would be -2, +1, +3. Okay, let's go back to the top. Look at our theorems. Fundamental theorem. We were supposed to have 3 roots total, do we? Yes. Number of positive real roots. We were either going to have 2 positive real roots or no positive real roots. How many did we have? 2. If we would have ended up with 3 positive real roots, we would know something's not right. Either we calculated how many we were supposed to have incorrectly or our roots are not correct. We were supposed to have one and one only negative real roots. How many do we have? Just one. And look at our possible list of roots. Is negative, these are all real rational roots, right? So we should find all of them in the list. Is negative 2 in our list of possibilities? Yep. Is 1 in our list of possibilities? Yep. Is 3 in our list of possibilities? Yep. So out of 8, 3 of them that we got were all in that list. Okay? You're not going to have all 8 as roots because we could only have 3 if you have 3 degrees. Is everybody cool with that? Yes, that's really awesome. Okay, let's do another one. So it'll go faster now, hopefully. Example 2. We have f of x equals 5x cubed minus x squared minus 5x plus 1. 5x cubed minus x squared minus 5x plus 1. How many total number of roots are we going to have? 3. What theorem told us that? Fundamental theorem of algebra. That's right. Sorry. All right, number of positive real roots. So remember, to find the number of positive real roots, count how many sign changes you have in the original problem. So first term to the second term, do we have a sign change?
No, yeah.
Yes, positive to negative. How about second term to the third term, sign change?
No.
Nope. Third term to the fourth term, sign change? Yeah, so how many positive real roots will we have? 2 or 0. Or I could say none. Sometimes we get confused with 0. We think we're supposed to have a 0 as a real root. 2 or none, or 2 or 0 real roots. That's it. That's the only possibility. Don't forget to reduce it by 2, because a lot of times we do, and then when we end up not having any, we get confused because we're supposed to have 2. Well, you're supposed to have 2 or you're supposed to have none, right? Number of negative real roots. And this one's easy to make the mistake on when you're substituting in that negative, so be careful. So remember, take the original, but wherever you see an x, substitute in a negative x, and then simplify. So be careful here. I'm subtracting x squared. Well, I'm subtracting negative x quantity squared. This negative was already there. The x I replaced with a negative x. Minus 5 times negative x plus 1. Negative x quantity cubed. Say negative or change to positive? Stays negative, and then when I multiply that negative times the positive 5, what do I get? Negative 5x cubed. Negative x squared, negative or positive? Positive x squared multiplied by the negative on the outside gives me negative x squared. Negative 5 times negative x, positive 5x, and then plus 1. All right, so first term to the second term, there's no sign change. Second term to the third term, we have a sign change. Third term to the fourth term, no sign change. So how many negative real roots will we have? Just 1. 1 and 1 only. No more, no less. All right, awesome. Now let's figure out what are our possible rational real roots. What is our p? Which number is p? 1. It's always the constant. And what is q? 5. So first of all, let's start by finding the factors of p. which are just 1, positive, negative 1. Anything else? That's it. All right, factors of Q. We're always going to have positive, negative 1, right? So always start with that. What else? Positive, negative 5. Anything else? That's it. So remember, to find the actual possible factors, we have to do P divided by Q to get our list. So what's 1 divided by 1? 1. So we're going to have positive, negative 1. And what's 1 divided by 5? 1/5. So positive, negative 1/5. 1 divided by 5 is not 5. It's 1/5. So this is our list of possibilities. It's not the factors individually. It's P divided by Q. So 1/5 might be the only real rational root we have, or negative 1/5. But when I'm doing my synthetic division, I'm not going to start by checking to see if 1/5 is the root, because I'm going to be multiplying fractions and adding fractions, right? But we might have to. But I'm probably going to start with either positive 1 or negative 1. So, what you want to try? Okay, 1 it is. And remember, get your coefficients from your original. I'm not going to rewrite it down here, but I've got 5, negative 1, negative 5, positive 1. If you're going to forget where you got those numbers, when you go back and look at your notes, make yourself a little note. So, coefficients of the original is how I'm getting these numbers. 5, negative 1, negative 5, positive 1. Then we skip a line and draw a line. Now remember how to start it off? Yep. First 5, we're just going to drop it like it's hot. Then what do we do with that 5? Multiply it by the 1. 5 times 1 is 5, and it's positive. I don't have to write positive 5, but I like to. Then we add and subtract whatever the signs are. Negative 1 and a positive 5 make 4. It'll be a positive 4, right? Then we multiply. 4 times 1 is 4. Add and subtract. Negative 5 and a positive 4 make negative 1. Negative 1 times positive 1 make negative 1. 1 minus 1 is 0. Is 1 a root? Yes, we just got lucky again. It's not always going to happen. Sometimes you might try 2, 3, 4, 5 of the roots and not find a solution. If the remainder is not a 0, it's not a root. Pick another one to try it. Pick another one to try it, okay? So let's write our reduced degree polynomial. So if we started with 3 degrees in the original, just take 1 off of that. So our first term will have 2 degrees. We'll go 2, 1, 0. So that would be 5x squared. The sign of the 4 is a positive, so positive 4x minus 1. That is our reduced degree polynomial. Hey, look, it's a quadratic. Do we know how to solve quadratics? Yes. Just because I might want to factor, does it mean that I'm going to be able to? No, but this one's factorable, so we're going to. But if you don't want to try and take the time, just go straight to the quadratic formula or go straight to completing the square, okay? So we know we're going to get 2 degrees from that, or 2 roots, because it has 2 degrees, right? Fundamental theorem tells us that. All right, so now we're going to solve the quadratic polynomial of 5x squared plus 4x minus 1. I will try, can somebody get that? To factor first. So if I'm factoring, is there a greatest common factor? Oh, I moved you. See, you couldn't see back there, so I know you sit back there, it should be okay. Is there a greatest common factor? Nope. What is A? 5. What is B?
4,
What is C?
-1.
Alright, so let's make our little T-chart. I need two numbers that multiply together to give me AC. What is AC? -5. And then add together to give me B. And B is +4. What's that? Say it again. Alright, let's try. +5 times -1 does give me -5, but that does not automatically mean that's our numbers. You have to check the right side. So 5 plus -1 does give me +4, which is what I was looking for. So we know since it works on the left side and the right side, we found our numbers. So make our little parentheses. Variables x. We'll put a +5 in one set and a -1 in the other. Will I need to divide and slide on this one? Will it make a difference? Yeah, because A is not 1, right? So I will divide or I will slide each of the terms that I got from the T-chart by 5. 5/5, is that going to be a divide or a slide?
Divide.
What do I get? X plus 1. -1/5, divide or slide?
Slide.
And can I reduce first?
No.
No, if I can, I must, right? But I can't, so slide the 5 on over in front of the X, and what do I get?
5x -1.
So I'm finished factoring, but have I solved yet?
No.
I'm supposed to get two solutions, how many, or two roots. How many am I going to get? 2. If I set x plus 1 equal to 0, what will that give me?
X equals -1.
So there's one of my roots. If I set 5x minus 1 equal to 0, what will x equal? 1/5. There's my other root. So at this point, I'm supposed to find 3 roots. I have found 3. I found 2. Once I found that reduced degree polynomial, and then I found 1 from the synthetic division. So my answer, my roots, least to greatest, I have -1, 1/5, and +1. All right, go back to the top. According to the fundamental theorem, we were supposed to have 3 total roots. Do we have 3 total roots? Yes. According to Descartes' rule of signs, we were supposed to have either 2 positive real roots or no positive real roots. How many positive real roots did we have? 2, so we're good with that. We were supposed to have 1 and 1 only negative real root. How many did we have? 1. All of our roots were rational roots, so they should all be in our rational list. Say if I got the square root of 2, that's not going to be in my list. But if I got rational real roots, they should be in my list. +1 and -1, they were in the list. +1/5, it was in the list. So the only one we didn't have that was our actual root was -1/5, right? Okay. So you see how knowing those things are helpful to your work. Anybody have questions? All right, I'm going to pause this and get it to save real quick, but I do want, so that you can try this on your own, just get out a sheet of paper and I'll give you one to try on your own.